In this lecture, we will go through some examples on frequency response. Okay, our first example has to do with the following transfer function. Given the transfer function of some filter, let's say h of s 30s plus 1 s squared plus 8s plus 15. Okay, we have to figure out the gain and phase characteristics. Okay, but first we will plot the pole zero diagram for this transfer function, and then we will roughly obtain the magnitude and phase characteristics in a visual sense on a plot. Okay, so here goes the solution. H of s, the transfer function, equals 30 times s plus 1. So the numerator polynomial is first order, so it's clear where the zero of the transfer function is. Okay, it's at -1. As for the poles, we have to figure out the roots of the denominator polynomial, and denominator polynomial, it's not difficult to see, can be written as in the following: product of two first order terms, s plus 3 times s plus 5. So that means we have a 0 at -1 and a pair of real poles, one at -3 and the other at -5. Okay, so therefore zeros, -1 poles at -3 and -5. And as for the gain, okay, and gain is what appears here, multiplying the fraction when you write both numerator and denominator polynomials with as monic polynomials. Okay, the highest order terms, s here and s squared here, they are 1. Okay, and then that thing is multiplied by something, and that something is what we call it the gain of the transfer function. Okay, in this case, gain, call it k, is 30. Okay, and then you take, what we do is we take this set of information and express them on the, or communicate them on the complex plane, and that's what we're calling the pole zero diagram. Okay, so let's squeeze it here. The pole zero diagram, therefore, is, this is the real axis, this is the imaginary axis, the origin. Okay, so we have a 0 at -1. Excuse me. Okay, 0 at -1. Remember that zeros are indicated by tiny circles, and we have a pair of poles at -3 and -5, and the poles are indicated by little crosses. So what we have is one here and another here, -3 and -5. Okay, so tiny circle, that means we have a 0 at -1, two tiny crosses, so that means we have poles at -3 and -5. There's only one piece of information that's left, and it's missing, and that's the information regarding the gain. So somewhere in the diagram we write that the gain is, okay, 30. And then by looking at this diagram, we can now reconstruct the transfer function h of s. Okay, so that was easy. Let's move on to the second part, B, where we will obtain some important properties of the magnitude and phase characteristics, and then using those properties we will roughly plot those functions, okay? The gain versus omega and the phase versus omega. Okay, so let's start with the gain. H j omega equals 31 plus j omega, then 15 minus omega square plus j 8 omega. Okay, so what we do is we're computing h at j omega. Okay, so that, by looking at that, first we can see what happens at very low frequencies. For instance, what happens at DC, okay? And then what happens at very high frequencies, that is, what happens to the gain when omega is arbitrarily large, when omega goes to infinity. So it's clear that the DC gain, Hj omega at omega equals 0 equals, plug in omega equals 0, so what we have is 1 in the numerator and 15 in the denominator, and here we have the gain 30 over 15, that produces 2, okay? And what happens as the frequency becomes larger and larger, so what happens as omega goes to infinity? Now, as omega goes to infinity, what we have is j omega dominates the numerator and minus omega squared dominates the denominator. Therefore, as for the gain, this fraction converges to omega over omega squared. Okay, since omega squared dominates omega, so what's happening is, as frequency becomes larger and larger, the gain converges to 30 over omega, okay? And that 30 over omega, clearly, when omega is very, very large, is 0. So, therefore, at very high frequencies, we see not much at the output side, okay, if h of s is transfer function of a filter. Okay, so we figured out what happens at low frequencies and then what happens at high frequencies. Let's also try to figure out, if we can, the maximum value that the gain attains, and also at what frequency that maximum value is reached. Okay, so let's figure out Hj omega max. Okay, so Hj omega, let's compute it, and then what we can do, we can just differentiate it, equate it to 0. We know that at max and min, the derivative should be 0. Okay, and then using that procedure, we can figure out both the maximum value and also the frequency at which that value is attained. Now, since we're going to differentiate to find the extremum point, it's better to work with the square instead of the gain, and note that whatever the frequency at which this is attained, the maximum value is attained, it's also should be the frequency for which the square of the gain is maximum. Okay, so therefore, to figure out that frequency, we can work with the square of the gain. So that equals 30 square, and then plug in s equals j omega. So the magnitude of 1 plus j omega square, which is 1 plus omega square, and here we have, okay, here we have 3 plus j omega, and then we take the magnitude square, so that produces 9 plus omega square, and likewise we have here 5 plus j omega, okay, magnitude square, which is 25 plus omega square. Okay, so that's the square of the gain, h omega, and then now we will try to figure out the maximum that that function attains. Okay, so let's introduce some notation which would simplify our analysis. Let, for instance, note that here we have only omega squares. Therefore, we introduce a new variable, sigma, which is omega square. Okay, in terms of our new notation, hj omega square equals 30 square sigma plus 1, and here we have sigma plus 9 times sigma plus 25, which reads 34 sigma plus 225. So now what we're going to do is we're going to differentiate this with respect to the variable sigma, equate that to 0, and that will give us the sigma value at which the maximum is attained. And then square rooting that sigma will give us the peak frequency, okay, omega max. Okay, differentiating that thing with respect to sigma and equate that to 0. So that produces, first of all, we can forget about this as far as figuring out the maximum frequency, because it is constant multiplying the thing, so it will not affect anything. Okay, and then what we're doing is we're now differentiating this and equating it to 0. Derivative of this is derivative of numerator times denominator minus derivative of the denominator times numerator, and then you divide everything by the square of the denominator. Okay, so we can forget about, because we're trying to figure out the maximum value, we can forget about that squaring the denominator part and concentrate on the numerator. So that produces, okay, that produces derivative of this thing, which is 1 times the denominator, sigma square plus 34 sigma plus 25 minus derivative of the denominator, okay, 2 sigma plus 34 times the numerator, okay, and this whole thing is divided by the square of the denominator, and then we're equating that to 0. In that case, we can forget about the square of the denominator, okay, only concentrate on the numerator. Now, solving this is a second order equation, okay, quadratic equation in terms of sigma, that produces sigma squared okay, sigma squared plus 2 sigma minus 191 equals 0. That's sigma plus 1 square equals 192, and that produces sigma equals square root of 192 minus 1. Note that we're only interested in the positive root because sigma is something square. Okay, so this is roughly 196, and then you take the square root of 196, that produces 14 minus 1, so that's 13. Okay, so this approximately equals 30. So what we have achieved is the following: take the square root of 13, and that's the frequency, square root of 13 approximately, at which the gain attains the maximum value. Okay, now let's figure out. Okay, so that means omega max, the peak frequency, is approximately square root of 13. Okay, now let's also figure out h omega max, which is, take this thing, plug in omega squared equals 13, and then take the square root of everything. Okay, hj omega max, therefore, equals approximately 30 times, okay, 1 plus omega square over 9 plus omega square times 25 plus omega square. We're taking the square root and plugging omega equals the peak frequency. Omega equals square root of 13, okay? And that approximately equals 4, okay? So that's enough detail for us to sketch the gain characteristics. We have what we have at now, what happens at low frequencies, what happens at high frequencies, and we also know the maximum value and at what frequency it's achieved. So let's therefore sketch the gain characteristics, and then we can move to the phase. Okay, so let's summarize our findings on a simple plot regarding the gain. Omega, Aj, omega. Okay, so we start from 2. Okay, and we're heading toward 0 as omega goes to infinity, but we're doing that in a non-monotonic fashion. That is, first we rise a little, we reach a peak, and then we start decreasing. And that peak is at 4, and happens to be at the square root of 13 radians per second. So roughly, this is the gain plot. Square root of 13 radians per second, and here peak is 4. Okay, Aj omega magnitude. Now let's move on to phase. So Hg omega, the phase of Hg omega equals the phase of the numerator minus the phase of the denominator, minus 15 minus omega square plus J8 omega. As with the gain, let's figure out what happens at low frequencies and what happens at high frequencies, and then that's more or less what we need, okay, to obtain the sketch for the phase. So Hg omega at omega equals 0 is 2, okay. Note that we're not talking about the gain, we're talking about Hg omega, the actual complex number. So therefore it's purely real, so that means at omega equals 0, the phase is purely real and positive, therefore the phase is 0 at omega equals 0, okay. So Hj omega equals 0 degrees. Okay, now how about very high frequencies? How about the limit of the phase as omega goes to infinity? Hj omega, so that equals limit omega goes to infinity of the numerator, which is 1 plus j omega, minus omega goes to infinity, the phase of the denominator, which is minus 15 minus omega squared plus j8 omega. Okay, so the phase of this is clear. As omega goes to infinity, this whole thing is dominated by j omega, the phase of which is 90 degrees because it's purely imaginary. And as for the denominator, as omega goes to infinity, this is the dominating term, a negative real number, therefore its phase is 180 degrees. So that means when omega goes to infinity, the phase is going to 90 degrees minus 180 degrees, so that's minus 90 degrees. Okay? So the phase therefore should roughly look like it starts at 0 and then it's going toward minus 90 degrees. So that seems to be a good approximation. But if you look at this thing carefully, we can still make our approximation a little bit better. Okay? And to do that, we have to observe the following simple detail. Okay. Observe the following. H j omega at frequency square root of 7 radians per second equals, okay, this is the phase expression. At omega equals square root of 7, what we have is 1 plus j square root of 7, the phase of this. Okay, so this is coming from the numerator minus, okay, if omega equals square root of 7, omega squared is 7, 15 minus 7, that produces 8. So what we have is 8 plus j, 8 times square root of 7. In other words, we have 8 times 1 plus j square root of 7. This 8 has okay, this 8 has no importance as far as the phase is concerned, therefore we can erase that. So what we have is the phase of 1 plus j squared of 7 minus the same phase, so that means at this frequency omega squared of 7 radians per second, the phase is 0. Now we start at 0, we're heading toward minus 90 degrees, but we have another crossing at 0. So that what that means is we start from 0, we have to rise a little, okay, reach a small peak, and then go toward minus 90 degrees. And then once, since we are positive and we're going to something negative, we have to cross the 0 degree line at some frequency, and that frequency we just observed to equal square root of 7. Therefore, this is roughly, but not too roughly, the phase plot, okay? Hj omega phase, this is the 0 degrees. And this is where we're heading, minus 90 degrees. We start at 0, and we're gonna head over there, but we make a little peak first. Okay, and then this frequency at which we cross 0 degree line, 0 degree axis, is square root of 7. Okay, now that's the end of our example, but before we end our example, I want to put an exercise and if you have time to work on it, you will see a very nice geometric relation between what we have obtained in part A, namely the pole zero diagram, and these gain and phase characteristics. Okay, so let's quickly remember what the pole zero diagram was for our example. Okay, it's the real axis, this is the imaginary axis, the origin. K is 30, that was our gain. Now we had a 0 and 2 poles. The 0 was at -1, and our poles, excuse me, our poles were at -3 and -5. Okay, now let's pick a point, and that point is purely, we pick a point on the imaginary axis, therefore it's purely imaginary, hence it equals j omega for certain omega. Okay, now to this point let's draw these vectors, okay, where the tail of the vectors are at poles and zeros, and head of those vectors, head of those arrows are at our point j omega. Okay, and let's call this angle here theta 1, and let's call these angles here phi 1 and psi 1 and psi 2. Okay, so those are the angles. Theta has to do with the 0, and these psi's, they have to do with the poles at -3 and -5. Also, let's give a name to the magnitudes of those vectors. Okay, alpha 1 is the magnitude of this vector here, and I'm going to call the remaining vectors R1 and R2. Okay, so R2 is the length of this vector from -5 to j omega. R1 is the length of the vector from -3 to j omega, and alpha 1 is the length of the vector from -1 to j omega. Okay, now link between the pole zero diagram and gain and phase functions is the following. It's not difficult to show that the phase h j omega, okay, equals theta 1 minus the sum of those two angles, psi 1 minus psi 2. Okay? And as you play with j omega, these angles, they all change, and then as a result the phase changes, and by looking at that change you figure out the omega versus phase of h omega characteristics. Okay, if you look at this expression closely in the pole zero diagram, you see that theta 1, this is no other than the phase of the numerator term 1 plus j omega, and this sum is no other than the phase of the denominator. Okay, and as for the gain, hj omega magnitude equals the gain here k times, okay, this ratio alpha 1 over r1 times r2. Alpha 1 happens to be the magnitude of the numerator term, and r1 r2 product is the magnitude of the denominator term, and also we have this 30. Therefore overall they make the gain at the frequency omega. Clearly, as you play with this point on the imaginary axis, as you change with omega, the gain changes, and that change gives you the function, okay, the magnitude versus omega function. Okay, now let's move on to our next example. Okay, we have the following filter topology. This is where we apply the input, and this is where we collect the output, okay? In a sense, generator side and load side. This is a passive LC filter. And here we have 2R, okay? 2 times the resistance here. Now, what we're given is the following information. H of S, VL of S over VG of S is a second order bandpass transfer function. Okay. So then suppose the resistance R is 1 ohm. So here we have 1 ohm, here we have 2 ohms. Provide 2 filter structures namely design what's inside that box and determine the element values so that the peak frequency or the center frequency is 1 radians per second. Okay. Furthermore, the half power bandwidth is 1/2 radians per second. Okay, and then we have B, scale the circuits. Okay, by magnitude and frequency scaling if necessary, so that the peak frequency or the new peak frequency is at 4 kilohertz and the resistance value R is now 2 kilo ohms instead of 1 ohm. Okay, so we carry the resistance value to a more realistic range. Okay. Okay, so we studied, you've seen earlier, 2 possible bandpass filter structures, okay, namely the series and the parallel connection. So let's therefore try both of those structures. In our filter 1, let's try the parallel connection, by which I mean the following. Filter 1. And inside our box we have a capacitor and an inductor connected in parallel as shown. Okay, so here we have 2R, this is R, LS and 1/CS, the impedances, plus minus VG, and this is where we collect the output, okay, VL. Now let's obtain the transfer function for that topology, and once we have the transfer function we can apply our design constraints and figure out what we need to figure out. Suppose, okay, let's figure out the equivalent impedance here, okay, that is we have a capacitor, an inductor and a resistor connected in parallel. Therefore, this whole thing can be represented by some equivalent or effective impedance. And once we have this impedance, we can compute the transfer function simply by a voltage division, which would be Z over Z plus 2R, which is the overall, which is the input impedance seen by the VG. So Z of S equals 1/the equivalent admittance, and equivalent admittance, since connection is parallel, is the sum of individual admittances, namely CS 1 over LS and 1 over R. CS plus 1 over LS plus 1 over R. Okay, and that can be shown to equal S squared plus 1 over RCS plus 1 over LC. Okay, and then transfer function can be produced by the following voltage division: Z of S over Z of S plus 2R. Okay, so let's continue with our design. So when H of S is computed through this voltage division, the result turns out to equal 1 over 2 RC S over S squared plus 3 over 2 1 over RC S plus 1 over LC. Okay, so clearly we have a 0 at the origin, and we have a second order denominator, so that's second order bandpass filter. Okay, and the general notation we used for such filter was Ks divided by S squared plus 2 alpha omega 0 S plus omega 0 square, where omega 0 was our center frequency or the peak frequency. Okay, now that produces the following: 1 over LC equals omega 0 square, peak frequency square, and the peak frequency we were told to choose 1 radians per second, so that means 1 over LC must equal 1 square. Okay, and 3 over 2 1 over RC equals this thing here, 2 alpha omega 0 or 3 over 2 1 over RC. That's the bandwidth of our bandpass filter, and we're told that that equals 0.5. Okay, 1/2. And finally, we were given that R equals 1 ohm. And this is enough information for us to figure out the parameter values, namely the inductance and the capacitance. R is given as 1. From this, we can figure out the capacitance value. Once capacitor value is figured out, we can figure out the inductance value from the very top equation. Okay, so C equals 3 farads and L equals 1 over 3 henries. Okay, so this parameter choice plus this topology, parallel LC filter, okay, or connection, produces the desired result. Okay, now let's also talk about the scaling. Okay. Now we are asked to place the new peak frequency omega 0 hat at 4,000 hertz. Okay, 4 kilohertz. So that makes 4,000 times 2 pi, 8,000 pi radians per second. Okay, from hertz we go to radians per second. 8,000 times 3.14 radians per second. Okay. And omega 0, this is omega 0 square. Omega 0 was initially 1 radians per second. 1 radians per second. Okay. Therefore, the frequency scaling factor is the ratio omega 0 hat to omega 0, which is 8,000 pi. Okay, so that's our frequency scaling factor. How about magnitude scaling factor. This is the desired resistance value, R hat, 2 kilo ohms, and this is the initial resistance value, 1 ohm. Hence, the ratio gives us the magnitude scaling factor, Km. Km should be R hat over R, which is 2000. Now, once we know the factors Kf and Km, we can now easily compute L hat, C hat, and R hat. Well, R hat is already given, so we have to compute L hat and C hat. Okay. So, L hat equals Km over Kf times the old or the initial inductance value, and that produces 2 over 24 pi henries. Okay, Km, Kf, they are here, and L is here, 1 over 3 henries. What else? C hat equals the initial C divided by Km, Kf. Km, Kf, they are here, and C, the initial capacitance value is here, 3 farads, and after scaling, this becomes 3 over 16 pi microfarads. Okay, and that's the end of our design. Now let's also consider the other possibility for our filter design, namely the series connection. Okay, filter 2, second design possibility. Okay, plus minus Vg plus minus output R Ls 1 over Cs, and we have here 2R. Okay. Again, the transfer function can easily be computed through voltage division. H of S equals the impedance here, or the resistance R, divided by the deriving point impedance, which is 3R plus 1 over Cs plus Ls. Okay, and that produces R over L S squared plus 3R over Ls plus 1 over Lc. Again, we have a 0 at the origin, and the first order numerator and the second order denominator, so that means, again, we have a bandpass, second order bandpass filter. Okay. This time, equations are as follows. 1 over Lc again is omega 0 square, and omega 0 initially was wanted to be 1 radians per second. Okay, so 1 over Lc equals 1 square, which is 1. The bandwidth 3 times R over L equals, okay, this time the bandwidth is, okay, here to alpha omega 0 equals 1 over 2, and finally R is 1 ohm. From here, since R is known, from here, from this equation, we figure out L, and once L is figured out, C is also determined. So it turns out that's L equals 6 henries and C equals 1 over 6 farads. Produces the or satisfy the design constraints of the initial design. But then we have to modify our design to by scaling so that it fits the final design requirements. Okay, and that's easy. L hat equals Km over Kf times L. Okay, Km was 2000, Kf was 8000 pi, And L is here, 6 Henry. Therefore, this produces 3 over 2 pi henries. Okay, that's the inductance value for the second design. As for the capacitance, it's C over Km Kf. Okay, C is here, 1 over 6, and that produces 1 over 96 pi microfarads. Okay, and finally, right, our desired resistance, okay, through which we computed the magnitude scaling factor to be 2000 equals 2 kilo ohms. Okay, so that's another possibility. Pick L hat, C hat, R hat, those values, and set the topology of your LC filter as this series connection.